you see a graph like this, there's a name for whenever you have weird graphs like this. It was semi-log plot. The important thing you need to know, if you're working with a semi-log plot, the important thing you need to know is the transformation that occurs that makes it happen. Now, just look at the values. You should be able to find out. Looking at the x's, do the x's look like they've been changed? If you look at the y's, do they look like they've been changed? Yeah, they're counting weird. How did we get these weird values? What we did is we took a log. I'm answering this question. What transformations occur? We take the log of the y values. So you take a log of the y values, a common log. So what does it mean to be a common log? Log base 10 of the y values, which means a lot of times you might see it written this way. You might see it log of f of x, because what does f of x represent? Y. Now, I want to make sure it's clear. Do we change our data? Do not change your data. Do not change your data. What do you change? Just the y-axis. Now, I want to point out, why is it 1, 10, 100, 1,000? Because the count by powers. 1 is the same thing as 10 to the power of 0. 10 is the same thing as 10 to the first. 100 is the same thing as 10 squared. You see how these lines, this bold line, this bold line, this bold line, they're counting by powers. Does that make sense? That's how it works. Now, does that mean I took 10, I took the y's to the power of 10? No, I did the opposite. I took the log of the y's, and it makes it look like that. Okay, so let's look at an example. What if we had to plot these points? So if I give you this, let me just create a table. How about that? And it's y equals 2 times 4 to the power of x. We'll plot maybe 4 points or so. 0, 1, 2, 3, and 4. So what corresponding y values will we get when we plug this in? What is 4 to the power of 0? What's anything to the power of 0? 1. 2 times 1 is 2. Okay. I plug in a 1. What's 4 to the power of 1? 4 times 2? Okay, we plug in a 2. What's 4 squared? 16 times 2? You can see the pattern now. What's happening each time? It's multiplying by 4. So 4 to the third power, that's 64 times 2. 128. And now if you plug in a 4, oh my goodness, it's going to be a big number. That's 64, 256. Very good. Times 2. 512. There's the data we'll plot. So let's go as best as possible. Now, is that 0, 0? Is the origin 0, 0? It's weird. It's 0, 1. So I need to plot 0, 2. I go up just one line. That's 0, 2. And then we plot 1, 8. 1, this is 8 right there. Because that's 1, 2, 3, 4, 5, 6, 7, 8. That's 1, 8. Then I would plot 2, 32. 10, 20, 30. 2, that's 2, comma 32. 3, 128. There's 100. How much is this right here? 200. So 128 is somewhere in there. 3, 128. And then finally, 4, 512. That's 100, 200, 300, 400, 500. It's going to be barely bigger than 500. 4, comma 512. Now, how does the data look when you look at that? Linear. It's very important you know that. Why does it appear to be linear? Because it's a log of the exponential data. Remember how I just said we take a log of the exponential data? That's why it looks linear. This is linear. I want to make sure you understand how the equation now is formed. This equation right here. Now, truthfully, what is the equation for this line? 2 times 4 to the power of x. If you're going off of slope and intercept, this does not have, this would act like your intercept, it doesn't have anything. You wouldn't think it's just one mark up. How you would find it here is you would do this. How it works, I want to make sure you know that. I'm going to call this y hat. Y hat. What I mean by y hat is the equation of this line right there. How the equation's built is this. The slope is the log of the base. That's the slope. That's your m. So I'm doing the equation of a line as far as mx plus b. That's what I'm doing here. It's the slope is the log of the base. Your y-intercept is the log of the a. I don't need a parenthesis around that 2. Sorry, it's just a 2. I'll do it like that. That would be that. So what do I mean by this? Let me just show you quickly on my calculator. If I go to calculator, and I type this value in, this is telling my slope. If you're like, what's the slope of this line? Well, it's whatever log 4 is. Log, I'm going to skip the base. What's it mean the base is if I skip it? Okay, my slope is 0.6. That means it has a rise of 0.6 for every unit you go to the right. Say it again. My slope is 0.6. Now remember, over here, it counts by powers. That means from this point, if I go 1 to the right, I go up 0.6. So if this is 1, this is 2, this is 3. Do you see how this goes up a little bit more than halfway between what looks like the x-intercept and this line here? Do you realize how I go up just over halfway? That's because it's the log of my base of 4, which was 0.6. Follow? So I'm going to write this down as approximately 0.6x. And then let's take log of 2 to find the y-intercept. Log 2. Now remember, this is 0, this is 1 on a normal graph. 0, 1. So this linear equation is given to me in terms of normal, how you would think of it. It's 0.3. Means you're just 3/10 of the way up. Close that off. And so back over here, plus 0.3. That would be the equation that right here. That represents how the data looks. Just to be quick, how would I get this equation I just wrote down back into this form? What's the opposite of a log? Exponential. So if I did 10 to the power of 0.6, 10 to the power of 0.6, what would that give me? I did 10 to the power of the slope. Would that give me the A or the B? B. That would give you the B. If you did 10 to the power of 0.3, what does that give us? A, 2. That's how you go backwards.